Okay. Okay, so again, good afternoon, everyone. So this is a lecture about deflection of beams. So this is the last topic for midterm exam number 2. For midterm exam number 2, you're going to get one problem associated with the second order differential equation, which we are going to discuss shortly. Now, these are just for reference remaining lectures, so we're going to try to stick with this schedule. I never realized that we have two holidays, April 2nd and 5th. I think that's Friday and Monday. Initially, I thought we are okay. We're a bit delayed, but okay. But right now, after realizing that we have two holidays, I think it's a little bit tight, but let's see how this works out. Okay, so going back to deflection of beams. So last meeting we discussed about deflection of beams, and if we talk about deflection of beams, it's all about okay, let's just change here. It's all about the y value, which is the distance of the beam after applying a force with respect to your reference x-axis. And you can also talk about the slope of the beam, which is this blue line right here. So slope is dy over dx, deflection is y. Now, we establish this equation here. We never derive this one. The derivation is in your book. But this equation applies, so we have d squared y, and again, your y is the deflection of your beam over dx squared is equal to your moment as a function of x, or as a function of the length of your beam divided by EI. So your EI is more or less constant. It's dependent on the materials. It's dependent on the size of your beam, for example. But this is kind of material dependent. Now, from this equation, we can integrate it two times. So we can integrate this equation on top once, equation number 1. And if we integrate that equation, we are left with this equation right here. And I should put really 2 at this point. So this would be the equation you have. So we integrate it instead of the second order. We have the first order, which is just dy over dx. And that's basically the slope of your beam. So if you're asked to calculate for the slope of your beam, which is how much it bends, so that would be the equation that you need. Now, it's not just about how it bends, how much deflection you get from your reference point. So you can further integrate this equation here. And once you integrate this one, you will get this second equation right here below. So again, this number 2 here should be on the top because this 2 and 3, they are the same. So once you integrate it, you are left with just y. And y is your deflection going back to your beam right there. So that would be, in the x is just x-axis. This part right here would be your y, which is your deflection. Now, once you do the integration, you're going to get the following equation. And the problem here is not exactly a problem, but take note that you have constant of integration. Now, once you have constant of integration, there's a certain value for that. And you can determine constant of integration by using boundary condition. And what are those boundary conditions? So we discussed those boundary conditions, and that's right here. Okay, so you can see y sub a at this point right here. So it depends on the type of beam you have. So if you have simply supported beam, you have A and B, which is pin and roller support. For example, it could be both pins or both rollers if you want. But if you have simply supported beam, you at point A and point B, you expect that it would not deflect from this reference x-axis. Okay, let me just hold a second. Okay, because my phone is ringing, but yeah. Anyway, it's connected to my Teams, so it's ringing right now. Okay. Okay, let me just wait for that. Okay, so now we have different boundary conditions. So at point A, we have y is equal to 0, and sorry for that, b is equal to 0. And because our phones for work is connected to Teams, so whenever someone is calling me, it would interrupt, and I'm using also Teams for lectures. So sorry for that. So we have simply supported beam the y at this point is equal to 0. And for overhanging beams, it's the same thing. You have your support reactions, you have 0 deflection or 0 y at point A and point B. And if you have cantilever beam, you would expect that, of course, B would move. And at support reactions at A, it's fixed. You can assume that your deflection in y is equal to 0 and the slope of the beam is equal to 0. And basically, why the slope is 0, your slope changes from one point to another because you have a curvature, which means if you apply a tangent line at every point at your beam, up to this point, it will just become flat right here, parallel to your x-axis, which means the slope would be equal to 0. So now we have different types of beams, and we can apply boundary conditions associated with that. And we started this problem right here. So now, so we have this cantilever beam. So we have a force P. And of course, in the exam, it doesn't necessarily have to be P. It could be a numerical value. And I'm just going to show you like the constants right now. But of course, in the exam, it could be, let's say, 5 kilonewtons or whatever number you have, or this could be a certain number. But for now, let's use a constant here because just to let's use constants right here, which is a problem in your book. Now, here we are asked to find the equation of the elastic curve. And what do you mean by equation of the elastic curve? We are asked to, so for letter A, so equation of elastic curve is just y as a function of x. So it's an equation that tells us what's the deflection at any point of our beam. So we have an equation, and whatever x we have, we can just substitute that x and we can get the deflection of our beam at any point. So number one, it's just an equation. Y is equal to something. Now, letter B is deflection at point A. Your deflection is y at point A, and where is point A? It's at this end. So once we apply force P, what would be the distance before and after the applying force P? And we are also asked to calculate for the slope at point A. So we can say that dy over dx at point A. Now, first things first, so if we talk about second order differential equation, everything, so let's forget about this this part for now. So if we talk about a second order differential equation, our objective is to get this one. So we have d squared y dx squared is equal to m as a function of x divided by ei. Our objective is to get this relationship of moment with respect to x. And how can we determine that equation? So now we can determine it if we have this beam right here. We can cut our beam, and before we cut our beam, first we have to put a reference axis. So in this particular case, if you have a cantilever beam, normally it would be at the end of your beam, which is at point A. And whereas my reference axis at this point, that's my y-axis, that's my x-axis, and my x is equal to 0 is this point right here at the end. That's x is equal to 0, and whenever I move from 0 point, it could be a value of x until I reach point B, which has a value of L. So at point B, you have x is equal to L. So now, but our objective is to get this m sub x equation. So in order for us to get that one, we have to slice our beam so at a length of x so that we can develop some equations. So in this particular case, I can slice my beam right here. And once I slice my beam right there or section it, I can get a certain length of x, and x could be is anything between A and B. So I have a value of x right there, and once I cut my beam, anything between A and B, I have a value for my shear, and I have a value for my moment. I normally use this convention whenever I cut, so that everything would be the same. So once you cut it, you have a certain value of a shear at the end to make it equilibrium. and you have a certain value of m. Now, how can I determine the equation as a function of m? I can sum the moment at at the end of my beam. So if I sum my moment at that point, I'm not going to call it any point right now, because yeah. So sum
Good
of
afternoon, Professor. I have a question.
yes, yeah, sure.
I can't understand what the symbols are when you have a moment, an arrow indicating that, and then you have two symbols that I don't understand what
Okay,
they are.
yeah, I can. This one. So this is your shear.
Yeah.
So that's an arrow going down. Let's say for now we can just assume any direction, but normally I use downwards. And so for moment, I have this moment right here, M. So that's a moment and shear. So once you have a beam, again, shear and moment diagram. So whenever you have a beam, you have to draw your shear, you have to draw your moment. That's always the case for beam. At least for me, that's how I imagine it. Yeah.
But Professor, the two little looks like K values on the
Where's that?
beside the. How do I indicate them? Right below the M. Yeah, those
That's
two.
just arrow. Yeah, I'm just pointing so that you can see what I'm talking about. Yeah.
Okay.
Okay, yeah. So normally
Okay.
I write arrows whenever I speak, because once I'm pointing here, you might not imagine where I'm pointing at. But yeah.
Okay, I see.
Okay. Yeah. So I'll just remove that. So I'll change the color probably. Yeah, and thanks for pointing that out. So that's V and M. So we have a shear and moment at the end, because everything has to balance out. And then what we're going to get here is, so if we're going to sum the moment at this point right here, we're going to get, that's our M exactly at the end. So that's a counterclockwise rotation. That's a positive number, let's say. And we have a force P at the end, like this one. And we have a distance X right here. So at this point, we have P times X counterclockwise. So it's plus Px is equal to 0. And then I can say that the moment at the end of my beam is M is equal to negative Px. So this would be my M as a function of X. And again, your P could be anything, could be 5 kilonewton if you want, 10 kilonewtons. So you can see that your M at this specific spot is negative Px. So now I establish my M as a function of X. I can now go back to my second order differential equation. So once I go back to my second order differential equation, I'm going to get the following. So I'll just substitute this M sub X to this point right here. And then I'm going to get the following. So I'm going to get, and I'm going to substitute EI right now. D squared Y Bx squared is equal to negative Px. So again, this part right here is your M as a function of X. Now we have this equation. So if we are going, if you go back to what we need deflection, we need slope. So basically we have to integrate our function. So we can integrate this one. And once we integrate this function right here, we're going to get the following. So we're going to get EI. Now this becomes dy over dx instead of square is now equal to, so now we're going to integrate this one. So I'm going to get negative 1/2 p x squared. So that becomes plus 1 right there, divided by 2 over there, plus c1. So now you have a constant of integration c sub 1. Now the question here is, what is c sub 1, which we don't know right now because that's a constant of integration. So let me just label the equations we have right now. So I can say that this would be my equation number 1, which is my m sub x. I can say that my equation number 2 would be substituting m sub x to my or equation number 2 is after integrating it. So now the question here is, how can I determine c sub 1? Let's go back to red. So now you can see that this is a slope right here. So again, this is a cantilever beam, and if you go back to our boundary condition, so that's the first thing you have to check. So if we have a cantilever beam, y at this point is equal to 0, your slope of your beam is equal to 0. Now, if we go back to our equation, we can apply the boundary condition. So at point B, which is at the end of the beam, we can say that at x is equal to L, so we can have dy over dx is equal to 0. Now, your constant of integration doesn't change from A to B. It's a constant, it doesn't change. So even though I'm going to apply any values associated with point B, it should not matter at all, so that I should be able to calculate what is C sub 1. Now, how can I calculate C sub 1? I have a value for my slope, which this guy right here. I have x equal to, I have a value for my x, and everything would fall into place. So I'm going to get the following after substituting this boundary conditions. I'm going to call it boundary condition number 1. So I'm going to encircle this one, and that's your boundary condition. So now we're going to get, now dy over dx is now 0, and that's the slope of a beam at exactly at your boundary condition, is equal to now 1/2, negative 1/2, p. Now your x becomes L, so now it's L square plus C1. We don't know what C1, and we want to determine what is this C1. And then eventually we're going to get C1 is equal to 1/2 P L square. And remember, your P is something that can be given in a problem, which is a number, 5 kilonewtons, for example, and L is the length of your beam, which could be given, and your C1, the C1 that we calculated is this one right here. And again, this is just substituting this, it becomes L, this one right here becomes 0, and then eventually we get this C1 right here. Question so far? And if it's fast, just let me know. I know that I'm trying to rush things, but the most important thing is for you to understand, and probably I'm missing something from my discussion. Question so far? None?
Professor, could you zoom in
Yep,
on BC, just that point at point B?
yep.
Oh, uh, what was what was the abbreviation of that for?
Boundary condition number 1.
Boundary
Yeah,
condition number 1. Oh, okay.
yeah.
I was just
Okay,
having. Thank you.
okay. That's okay. Yep. Okay, any questions? So now we have C1 as equal to this 1/2 PL square. And if you check the equations, so we have a C. So if we go back to equation number 2, we know what's C1, and we have a slope dy over dx. So we're looking at equation number 2. So we have value for C1. Dy over dx, we can get the slope of our beam at point A. And at point A, and why do we pick point A? Because it's asking the problem. So deflection, or sorry, slope at point A. So at point A, we know that x is equal to 0 at that specific point. Now, if I know that my x is equal to 0 at point A, I can substitute it to my equation number 2. So use equation number 2. Now, if I'm going to use equation number 2, I can write EI, and I can say dy over dx, and that's the slope at point A. So now we are referring to point A, and that's equal to 1/2 P. Now our x is equal to 0, so that becomes a 0 right there. Now plus C1. And what is C1? C1 is 1/2 PL square. And you can imagine that this guy right here would become 0, because that's multiplied by 0. And eventually, what you will get is the slope at point A is equal to PL square. And then you have divided by 2EI. So that would be your answer for letter C. So So this is for letter C, and you have a slope at point A. Question so far, because the first after you integrate your second order differential equation, the first thing that would pop up to you is dy over dx, which is the slope of your beam. So now that's dy over dx. So now we have deflection, which can be obtained after integrating the second order differential equation twice. So from here, what we can do is integrate again the equation. So let's go back to equation number 2. I call it 2 or 3. I can call this one as, yeah. Okay. Just so now we can rewrite equation number 2 into, and now that becomes equation number 3. And why do we have to rewrite? We're just going to substitute C1 is equal to 1/2 PL squared. So your equation number 2 becomes EI dy over dx, and that's the slope, is equal to negative 1/2 px squared plus 1/2 pl squared. So that's our equation number 3. Change it to blue, and that's equation number 3. Now from equation number 3, because that's our C sub 1, we can now integrate this one further and then get our deflection. So integrate. And once we integrate this one, we are going to get on the left side of the equation, that's now EIY. Now that would be equal to, so now this is squared, and you know that would become raised to 3. This would become x, but let's write it down. So that would become negative. So you have to review your integrals. So that's negative 1 over 6 p, oops, I'm pressing something, px raised to 3 plus, now this becomes 1/2 pl squared. Now you have x right there plus c2. Now your c2 is unknown for this equation. You go back again to your boundary condition. Now I have the second boundary condition for my cantilever beam, and I can say that my deflection at point A, so at point A, at point A is equal to 0. In our case, it's not point A, it's point B. So the deflection at point B is equal to 0. So at point B, which is your boundary condition, I'll call it BC, boundary condition number 2. So I have boundary condition right there. And we have at x is equal to L, which is the full length of the beam. Again, this is your reference axis from 0 up to L. So now I refer this one to L. Now, if you're talking about A, that's x is equal to 0. Here, it's x is equal to L. Now, at that boundary condition, my y is 0. I have deflection is equal to 0. Now, using this boundary condition number 2, I can substitute those values to my equation. So I have L, I have 0, I have y right here would become 0, I have x right there, and then I should be able to calculate my c sub 2. And now let's do just that. So now we don't know what is c2, so we can say that c2 right now is a question mark. We don't know what c2. So at point B, that's the value. So we can substitute, and then we can substitute this one to our equation. Yeah, let's still call it equation number 3. So we have now EI now becomes 0 is equal to, so now we have x is equal to L, so that's negative 1 over 6 P L raised to the 3 plus 1/2 P L squared times L, so you have another L right there, plus C2. Now, I have this 2. I can now calculate for my C sub 2. And my C sub 2 is just equal to negative 1 over 3 p L raised to 3. So that would be my value for C sub 2. I can now substitute C sub 2 to my I can substitute it on this equation right here, and then I have now the following equation. So now substituting C sub 2, we are going to get EI y is equal to negative 1 over 6 p x cubed plus 1 half p L squared x. Now this becomes C2, so that's now minus 1 over 3 p L cubed right there. So I have this equation using the value of using the calculated C sub 2. And if you look at the question right here, you have find letter A equation of the elastic curve. And remember, equation of the elastic curve is y is equal to a function of x. And this particular equation would solve your problem. So now I can say that my y, and this is just simplifying the equation on the top. So that's, maybe you can see it. So that's P divided by 6 EI. So I transposed my EI right there. I put the negative sign inside my parenthesis. So x3 plus 3L square x minus 2L cubed. So now I have this equation of my elastic curve, which answers the question here, right here, which is letter A. Now, how did I know it's the equation of elastic curve? I look at my constant. So your P, if we're going to look at one by one, so your P is just your force. It could be given in a problem. That's two constants right there. Now, I can obtain any value of deflection at any point of my beam, which means I can substitute any value in between A and B, and I should get my number. And take note, your L is just the whole length of your beam. So by using this equation, it defines the behavior of your elastic curve. So this would be the answer for A, which is equation of the elastic curve. Question at this point. So now we answered already A and C. We haven't answered letter B yet, but you will see how the equation on top works. Any question at this point? Nope. Okay, so now let's go to this question here, deflection at point A. Now, remember that the equation of elastic curve can determine any deflection at any point, which means the equation on top can be used to solve the problem at letter B, which in this particular case, if we talk about deflection at point A is, so remember that at point A, and let's change the pen. My notes become so colorful that, yeah, there's no system really in terms of color coding there. Sorry for that. So, okay, so we have point A. So we have at point A, we know that x is equal to 0. That's our reference axis. Again, the most important thing whenever you solve this type of problem is where is your 0 point. In our case, we assume it's at point A right here. Now, by knowing that x is equal to 0 and using y is equal as a function of x, which in this case, that's the equation on top, I can substitute x is equal to 0 and I should be able to solve the problem, which in this particular case, if I substitute the numbers, you can easily imagine that this would be the equation. And I'm going to write it. So EI is 3 plus 3L squared x is 2 raised to 3. This becomes 0 and that becomes 0 because at point A, x is equal to 0. So that those two terms become 0. And eventually, you're going to end up with the following. So here, y is equal to negative p L to the 3 divided by 3 E I. And if you want, you can put y sub A. That means that that's deflection at point A. And that would be the answer for letter B. Any question so far before we move to the next problem? Question? Everyone can follow? Or is this something discussed in mechanics one? Probably.
So just to be clear, Professor,
Okay.
the x starts x equals 0 starts at A. It's something that
Yep.
uh I've been confused all over until I realized, wait, no, it's just you have it the opposite.
Yeah, it's the opposite
So
way.
in other words, just to be clear and not get convoluted, at A x is 0, and then at B we have that length L.
Yep. X equal 12. Yep.
Is it always that procedure where we would have a, well, I guess for different beams we would have different
Yep.
effort, but is it
No,
always from left to right?
you
The
will notice this once you solve this one, but normally for cantilever beam, you want to solve from this one. But most of your problems, I think I'll do it left to right. I'll tell you if not, but usually it's from left to right. But for
I see.
cantilever beam, it's usually left. Normally, if you solve both ways, that's fine. Depends on each problem, but the other one would be much more complex. The other one would be much easier. In this case, that's the easier path.
I see. Thank you.
Yeah. Okay. Any other question? Okay. So if none, let's go uh, uh, problem number 2. So now we are given with this beam with a certain, again, we're still in the second order differential equation. So we have this W distributed load. We have points A and B. We have at point L. And the question here is find equation of elastic curve, which is just basically y is equal to an equation, which is a function of x. Now we have also B, which is an extra here, maximum deflection. And what do you mean by maximum deflection? So let's imagine that we have a beam which could be bended this way. Now, if you imagine this beam, and that's your reference line, your maximum deflection is at this point. Now, it could be in the center, it could be not, depends on whatever load you have on top. Now, how can you determine where is your maximum? If you have this type of beam, imagine that you can calculate the slope or you can measure the slope of the beam at any point. You just have to apply a tangent line. Now, exactly at the maximum deflection right here, you can see that your slope, dy over dx, is equal to 0 at that maximum deflection. We're going to apply this concept in this particular problem so that we can determine the maximum deflection using this. It's not necessarily your boundary condition, but this is the condition wherein you get a maximum deflection, and it changes from one problem to another. Of course, you may have a lot of slope which is equal to 0 if you have this kind of beam which could deflect different ways, but I'll not give you that complex for sure, because your slope here is 0, your slope there is 0, slope is 0, slope is 0, so you have 4 different points where the slope is equal to 0. But this for this particular problem, you can easily imagine that this beam could deflect this way because of that load, and your maximum deflection is somewhere in the middle, for example. So now let's solve this particular problem. Okay. Okay, so problem 2. And if I'm going to give you a problem in your midterm exam, should not be too difficult right now because we just had some introduction. Later on, you will see that this process becomes much more complex, I would say, with method of superposition and indeterminate beams, for example. But let's take a look at this problem number 2. So we have a simply supported beam. We have at point A, you have a pin connection. You have a roller, point B, and you have a distributed load, which is, okay, which we can call W right now, or omega. Now, we have, okay, let's remove that A. Sorry for my handwriting. So now, we have this particular beam, and right now, the first thing that you have to do is what would be the forces in the support reaction? Because even if you slice the beam to the left or to the right, so for example, if you just take the left or right side of your beam after slicing it to determine your moment as a function of x, if you take this, or even you take this one, you can imagine that I need a force at the left because this one produces a reaction at A and reaction at B. Now, in the previous case, if we go up to the previous problem here, we don't have that problem because we took the left side of the beam, which has a value of P, because it's if you go back here, we have a force P, which is kind of given. Now, if we take the other side, of course, we have to calculate for forces, support reactions at B. So that could complicate things, and that's one of the reasons why we pick the left side of our beam in this particular case. But for this one, I think when you solve it, picking on the left or right side, the complexity should be almost the same. But right now, let's look at this one. So we need reactions at A, and we need reactions at B. I'm not going to solve it right now, but what you can find here is if you want to get the supports in A and B, so this would become WL. At this point, you're going to calculate 1/2 WL, and this would be 1/2 WL, and that's pointing upwards. So that would be the support reactions that you are going to calculate. We're not going to do it for the sake of time, but I hope everyone knows how to do it. Of course, your distributed load exerts a force which is at the center. When you calculate, let's say, calculate the support reaction, so it's WL, and then of course you can get moment at point A or moment at point B, sum it to 0, and then you should be able to get the following numbers. So now you have R sub A, which is 1/2 WL, and it's pointing upwards. And you have R sub B, 1/2 WL, or omega, I'll just call it W, which is pointing upwards. And now I can now go back to my original beam using this number. So how can I go back? I have this distributed load. With my omega right there. And I have here it's 1/2 WL. I have 1/2 WL. Now, our objective is to use the second order differential equation, v squared y dx squared is equal to m m as a function of x divided by EI. Now, we need to take this m sub x right there. How can we do it? We have to cut our beam and find the number. So I can now cut my beam right here. And if I cut my beam with a length of x, in this particular case, again, I'm going to assume that my x is equal to 0 is on the left side. So change the color. So this would be my reference axis. So that's x is equal to 0. This point, that's my x-axis, that's my y-axis. So that's x is equal to 0. So now I can cut my beam, taking the left side of the beam, and find the values for, okay. So now if I take the left side, and my left side has, I'm going to call it RA for now, R sub A. Now I already cut my distributed load into length x, so this would be length x, but that's still omega right there. Now this would be the basis of my, so that's V, and then I have my moment right there. Now I can establish my moment equation using the following. So I can sum my moment at the end of my beam, say right here, and then I can find the numbers. So once you sum the moment at this point, it's equal to 0, what you will get, just checking the time if we have enough time, you can do this as practice, but what you will get is the following. So your m is equal to omega L over 2 x, and we're going to discuss it one by one, minus 1/2 or x over 2 wx. So how did we got this number? How did we get this number? So your r sub a is equal to 1/2 wl. So now I have length of x. So from at the end of the beam, I have this full length of my beam up to point A. So I have x times whatever r sub A is, and that's kind of a negative number. So you can easily imagine that I just transpose it there, but from there, but that's a negative number. So that's WL, 1/2 WL times x. So that's my first term for my moment. How about for my second term, which is this guy right here? Now, take note that your WL now exerts a force which corresponds to W times X. So initially, you can imagine that this omega right here is just W. I call it W for now. Sorry, guys, but to make it simple, so W times L. So initially, this distributed load right here is W times L. But for this particular case, now we cut along a section so that Wx is now your distributed load in my section piece. Now, this Wx is acting at the middle of my beam, which is x divided by 2, which means if I'm going to sum my moment, and this is now a very dirty equation, but if I'm going to sum my moment, you would imagine that I'll get the following. So I have L2x plus x over 2, and that's my distance, and that would be the general equation we get, and that's why we end up with the equation is equal to 1/2 Lx plus 1/2 Wx squared. And take note, just combine two. So this would be now my m as a function of x. And here you can see the most critical thing when you are calculating second order differential equation is what is my m as a function of x. In this particular case, that's what it is. Now I have my m. I can now substitute it to my d squared y dx squared is equal to, I'm going to transpose e times I on the left side. Now I can write the equations 1/2 Lx minus 1/2 dx squared. So I have those following equation. Now that squared, I want to determine my slope and deflection, because we are talking about equation of the elastic curve. So we want y is equal to a function of x. So I have to integrate twice. So let's try to integrate twice and not worry about C1 and C2 for now. So let's integrate. So integrate that equation there. So we are going to get the following. So we have EI dy over dx. So now that's 1. Now I'm going to get negative. Okay, why it's at x 3. Yeah, okay. They just move it down. Okay. Anyway, so that's negative 1 over 4. I moved the terms right there, so I got confused. WL x squared minus 1 over 6 WX3 plus C1. So I have now a C1 term which is unknown right now. Now I can integrate it again, and then I'm going to get C2. So let's integrate it again. Because we want the equation of elastic curve, which is y as a function of x. So once we integrate again, we are going to get the following. So
where's the
EI
negative coming from on the first term?
First term. Oh, that should be positive. Yes, thanks. That should be positive. Yeah, thanks. Yep. So the second one should be negative, because in my notes I mix it up. So the first part is negative. But thanks for pointing out. Any question? So now it becomes E times Y. Now we integrate it again. So now that becomes x raised to 4. And you will imagine that this will become a little bit mess, not much. It's not too complex in terms of integrating it. So Just be very careful when doing this one, and you'll see that everything. Okay, I mix it up again. Sorry, because in my notes I have the other way. So this should be 12 x3 minus 1 over 24. That's a minus sign. X4 plus now C1x plus C2. So I have now two constants of integration, C1 and C2. So now, yes, we have y is equal to some sort of equation, but we don't know what's C1 and C2, which is one of the most important things. So we don't know C1 is question mark, C2 is question mark right now. So the first thing is, let's look at the beam and let's define what's the boundary condition. And you can see that this is a simply supported beam, and you can go back here. So you can see that, okay, at point A, y is equal to 0. At point B, y is equal to 0. And maybe we can use that to calculate for C1 and C2. So let's do that one. So let's say we assume that at point A, so your point A at this particular point is x is equal to 0. Now your y is equal to 0. Now, by looking at this one, because your question, you can question that how can I tell if I should use point A or point B for my boundary condition? If you look at your equation, I need to zero out this C1 term so that I can take C2. Yes, you can do it the other way, but that will be much more complex. You can still arrive with the answer. But the simplest way is if you look at the equation, if my x is equal to 0, this term will be 0. I can calculate my C2, which in this particular case, at point A, x is equal to 0, y is equal to 0, and now I can calculate for some numbers. So that gives you, now that becomes 0, and then you can easily imagine that the first term becomes 0. The second term becomes 0 because you have x right there, plus 0, and then plus C2, and that gives you a C2 value of 0. And that's the real value of C2, which is equivalent to 0. Now, I have value of my C2. I can substitute it to my original equation right there. But I don't have C1 yet, so how can I determine my C1? So I have to use, so I'm going to call it boundary condition number 1, and I'm going to use at point B, my x is equal to the full length of my beam, my y right there is equal to 0, and I can call it as boundary condition number 2. So that would be the condition for my point, my second boundary condition. Now, I can apply this boundary condition again, going back to my original equation there. So, and then I'm going to get the following. So I'm going to get I times 0, because the y there is 0, and that's equal to, so now your x becomes L. So the first term is now 1 over 12 L times L raised to 3. And you can easily imagine that becomes raised to 4 plus, or that should be, I wait, okay, because I wrote it the other way, so I'm keep switching around. So minus 1 over 24, that's W L. Now, you can easily say that this is L raised to 4 plus C1 times L plus C2, and you know C2 becomes 0. Now, once you work your equation from here, you'll find that your C1, once you simplify the equation, is equal to negative 1 over 24 WL raised to 3. Just checking. Yeah, so you will get this value right here. C1 is equal to, I think I'm missing something. This becomes L, the 4. Okay, now I got it. Yep. So you will get C1 is equal to this value right here. Now I can substitute that number to my original equation. So now I can go back there and substitute to my y, and I'm going to get the following. So this is now a simplified form because it's 220. So this would be, and I'm not going to discuss the last point because that would be much more complex and will not be included in your midterm exam. So x4 plus 2lx3 minus L3x. And you can see this is my equation, y as a function of x, which means that I can substitute any value of x. I can determine what's the deflection at any point at this particular beam. So that concludes this concept application number 2. We never covered this maximum deflection. We may or may not in the next meeting, but you have a quiz number 3 and midterm exam on Friday. So I'll stop right here, and yeah, so I'm going to end it here. But before we end, this is the one I uploaded on the 2L. So this would be the problems for both quiz number 3 and midterm exam. So for quiz number 3, you have a design of transmission shaft and combined loads. Of course, I'll try to minimize the calculation time as much as possible because it's only 1 hour exam, but this would be the problems. And for midterm exam, which would be on Friday, that's a 3-hour exam. It consists of 5 problems. So we have transformation of stress and strain, theories of failure, principal stresses in a beam, combined loads, deformation under transverse loading, which is second order differential equation. That's what we discuss right now. And you can see that design of transmission shaft is not included in midterm exam, but it may be included in the final exam. So just keep that in mind. So you can miss this one for your midterm, but take note, this is included in quiz number 3 and might be included in your final exam. A question, I'm going to stop the recording. Any question, class?
Just a quick question.